Good morning. I'm Wakiyama from Institute of Environmental Radioactivity in Fukushima University. My background is hydrology and soil science, and so today's my topic is related to Riverine cesium dynamics as titled. I want to start with looking back the fundamental things of Fukushima-derived radionuclides. As you know, substantial radionuclides were released by the accident, and the major radionuclides are iodine-131. Sorry, I will repeat. Hello. Major iodine-131, cesium-134, and 137. They are all gamma emitter and reflect to ambient dose. Of these three radionuclides, iodine-131 and cesium-134 were almost removed due to their short lives. And about 3 to 6 petabecquerel of cesium-137 was deposited on the terrestrial environment according to numerical simulation. And now 11 years have passed more than 20% of cesium was removed by its physical decay. And I estimate 10% of cesium was removed by decontamination. And 2 to 4%, it's my estimation, cesium was removed by wash off through rivers. So my interest is this riverine dynamics. So after the deposition, cesium is exported from each landscape in river catchment associated with water and sediment discharge, then reached into river and then ocean. In river water, cesium is distributed into two fractions. One is particulate fraction, which is transported together with the suspended solid, and another is dissolved fraction. The graph shows long-term trend of cesium concentration in river water, dissolved and particulate. And they were observed by our colleagues at the midstream of Abukuma River. So they are both decreasing. The dissolved cesium, both dissolved and particulate cesium concentration decreased to at least 1/10 compared to early years after the accident. As Fukushima has a steep topography and large amount of rainfall, high flow events frequently occur and export cesium. As cesium has strong affinity to soil and sediment particles, substantial cesium is transported in particulate fraction. Previous studies observed a very high ratio of particulate fraction up to almost 100% during high flow events. And the majority of cesium can be washed off even in a single high flow event. For example, only one typhoon event in 2011 exported 60% of annual cesium flux from Abukuma River. So understanding cesium dynamics during high flow events are important. And then the recent study indicated that particulate cesium input during a huge rainstorm elevated the dissolved cesium concentration in coastal seawater. This is due to cesium desorption resulting from ion exchange between suspended solid and seawater. For example, after the Typhoon Hagibis, Takata et al. Reported that elevation of seawater cesium concentration due to increased contribution of terrestrial cesium from rivers. And the desorption of cesium was up to 100 times higher direct dissolved flux from the Abukuma River. So understanding the connection of cesium dynamics in terrestrial and ocean environments get more important. However, there are still few cesium dynamics investigations at the downstream site. This slide shows catchments, river catchments on the map of spatial distribution of cesium deposition in Fukushima. Total catchment about 9,000 square kilometers. The largest river is Abukuma River. You can see quite contaminated catchments around the Fukushima Daiichi nuclear power plant. These river catchments are main targets of this MITATE Lab. These, for example, Mano, Nida, Ota, Odaka, Ukedo. Which this side we went through. Yes, this excursion. Such varieties of scale, land use composition, geology, and soil types are expected to result in different cesium dynamics during high flow events. So I want to know what the characteristics determine the cesium dynamics. So I'm conducting a comparative study of cesium dynamics. For better understanding cesium dynamics, I'm conducting a comparative study for high flow events based on sampling campaign during the event. I'm discussing factors controlling cesium concentrations in terms of its temporal variation, relation to properties of water and suspended solid, and use land use effect. Also, I evaluate the cesium fluxes, including potential cesium desorption from suspended solid to the ocean. So the slide shows my to-date sampling campaign. I collected more than 10,000 liters from the rivers to date so far, accounting for 30 data sets, and the number is still increasing. Today I would like to show one of my researches, the river catchments, which are of interest of MITATE Lab. So, I show a case study based on our publication. This study, the study site was the Niga, Ukedo, Takase rivers in the Hamadogu area. They were heavily contaminated by the accident. I conducted river water sampling at the downstream point in these basin catchments during one event in September 2019 and two events on July 2020. This is the photo of the photo taken by the peak discharge phase on the rivers. The 30 liters of river water was collected using the bucket from bridges for 6 to 8 times per event and per site. This graph shows results in all rivers and events. Blue line shows the water discharge. Black one is suspended solid concentration. Red one is cesium concentration in suspended solid, and blue one is dissolved cesium concentration. The data are from Nida, Ukedo, Takase, and 3 events. So I will skip details, but based on this result, I explored factors controlling cesium concentration during the event by examining correlation between both cesium concentration and water sediment properties. For example, conductivity, particle size distribution, or something, and land use effect by use of stable isotopes. So this is an example of examine land use effect. To see land use effect, I plotted the cesium concentration against delta in nitrogen 15 as the index of the contribution of sediment source. So cesium concentration in suspended solid tended to be high with low delta value in the event of September 2019 for all rivers. The relation suggests that the contribution of forested area elevated the cesium concentration in suspended solid in the event. And the event in September 2019 was the most erosive event of all three events. That these results suggest that the land use effect may depend on rainfall intensity. So these hypotheses should be tested by further analysis, for example, numerical simulation or fingerprinting. But this kind of analysis could be helpful as with unveiling the processes. We also calculate the cesium fluxes based on the cesium concentration and hydrological data. Each event was separated into 6 or 8 times, depending on the sampling times. The rate of particulate and dissolved flux were obtained by multiplying based on this equation. For example, this table shows the particulate and dissolved cesium fluxes during the event of September 2019. Several gigabecquerel of cesium were exported to ocean, mainly in particulate fraction. These flux account for cesium in order of magnitude of 0.01 or 0.0001% of total cesium deposited on each catchment. Now, okay. So, furthermore, I looked at the relation between cesium flux and the rainfall properties to know the response of cesium in each catchment in relation to the land use composition. The vertical axis represent ratios of particulate and dissolved cesium fluxes to the cesium deposited in the catchment. The lateral axis shows USLE's R factor, which consider amount of and intensity of rainfall. The dissolved cesium fluxes were similar in each other, but for the particulate fluxes, we can see neither river show a relatively sharp increase followed by Takase and Ukedo River. The greater sensitivity of the Nida River than Takase River could be attributed to the smaller ratio of forest cover in the catchment. The low sensitivity of the Ukedo River is due to the effect of the Ogaki Dam. These results confirm catchment characteristics here at forest cover and dam reservoir control cesium fluxes. This way, I am exploring the relationship between catchment dynamics and cesium dynamics. Catchment characteristics and cesium dynamics. So we have another data set. It was the sampling campaign was done during August 2006 and October 2017. These data sets allow us to evaluate transportation processes of cesium in single river basin. I'm preparing the manuscript to be submitted to any of the journals. I hope data will be available in near future for further analysis. So still I'm going on the sampling campaign. So as a summary, this slide shows my strategy for the MITATE Lab. My main work is sampling campaign during high-flow events, and the final goal is to reveal relationship between catchment characteristics and riverine cesium dynamics. I will continue sampling campaigns and data publication. As fruit of these investigations, hydrological data will be available for model development, and some suspended solid samples will be available for source analysis. This way I can, I hope I can get feedback from the MITATE Lab. So it's all. Thank you for your attention.